So, canonical ensemble. So, those are the relation between thermodynamics and microcanonical ensemble that I given to you. I have given in the book certain problems, and I should mention to you that the entire solution book, all the solution of the problems are, I think one of you probably should work out in the class the problems. Entire problem set that is now available online free. If you have bought a book or anybody in the bought book, then you will be able to load the solution book. Yeah. So, and that solution book itself is about 200 pages, because there is a huge number of problems in this book. Okay. But you need to do the solution, because there are examples, there are problems which let you calculate omega and they calculate the properties. So, that is very essential part of the problem. Now, going over to canonical ensemble. Canonical ensemble now is the ensemble where the system is characterized now by NVT. So, you cannot change number, that is kept fixed. You cannot change volume, kept fixed. So, your volume is fixed. Now, so these are, well, the volumes are different, NVT, NVT, all are the same, and I am thinking of systems of ensemble, but the energy is changing now. So, the systems are connected with the bath. Now, we will do a beautiful mental construction that gives it, which is how to construct. So, basic strategy that gives it is the following. So, here we have number fixed, volume fixed, but energy exchange is allowed. Energy exchange allowed such that temperature is constant. So, you put it in a bath, and we in chemistry always do these experiments. We put it in a bath and to preserve the constant temperature. Now, then how did Gibbs did the calculation? Okay, now let me first ask you one thing, that when I let my energy constant go, which is, we grew up with the conservation of energy and we constant energy, we let it go. We let it go and replace it by a constant temperature. What is the change in this microscopic state of the system? Yes, absolutely. So, it can have many different energies. So, conservation energy is gone. Conservation energy is a huge constraint. All of them, they are constraints. But we work in a natural system or everywhere in the world with constraints. But here we let go the energy constraint. We are having in temperature. So, we let a macro variable go or extensive property go and replace it by an intensive property. Okay? So, what will happen now to the number of microscopic states? It will increase enormously, right? Okay. Now, this is an example, I believe is a very nice example. Okay. So, basic idea then is the following. These are not the best pictures, but we worked around with the pictures. The way it is canonical ensemble is NVE. So, I have a huge number of systems, I can put them together and I can, this is a construction gives it. So, we will come to that construction in a minute. This is I think one of the best thing in this whole of statistical mechanics. Here now I have the same example, my 4 systems, but now I make the energy levels change. Okay. So, now here energy is 6, there 8, this is 10. I have same energy levels, but now before I had only 4, right? I had only 4. but now I have this additional microscopic states. You are keeping the energy temperature fixed from outside. You are putting it in a bath. You know the temperature, just like earlier I knew NVE, that was my choice of my system. Here my choice of variables is NVT. So I have the systems which are same as number of each okay, in my system NV and T, that is, this is very standard experiments we do, that we have this number of volume and density fixed, total number of in a beaker, total number of then in a volume in a cell, volume is constant, then I put it in a outside temperature. So as an experimentalist or in my thought experiment, I can always keep these three fixed from outside. So they are fixed from outside means what? Connection to both of you asked the questions, that means I am freedom to vary these things. I do not have freedom to vary other things. I have freedom to vary these things, like I had freedom to vary NVE, and as a varying NVE, pressure is varying. Here also I have, these are my three independent variables. Okay. Now I do not have energy conservation, energy constant. However, I know if I keep the temperature fixed, then energy is getting exchanged. The system is exchanging energy with the bath. If the system is changing energy with the bath, then I have different energies. So as the different energies are there in the same number of microscopic states, because the system is the same, I will have the microscopic energy levels. I will have many more. There I have 4. I have many more microscopic states. But of course, let me ask you a question. Of course, constancy of temperature and variation of energy allows very different states. But there is a very powerful, very powerful equation, actually one of the most important equations that comes out of statistical mechanics, that came out of Boltzmann's work, that allows you to say which of these arrangement is more probable. Which is that? So when I allow energy to change, listen carefully, I think I am not formulating it well. I am telling you I am allowing energy to change, but systems always have a spring in them. Systems, just like volume, there is a spring, and in energy there is a spring. And I tell you the spring in energy is the specific heat. Spring in volume is the isothermal compressibility. Okay, these are all the springs, that means which hold system together, does not allow it to change. Actually, you can write down the free energy or any as a function expansion, and you can see that they are first order is 0 because of the minimum energy, free energy minima condition. Second term of this we call it response function, which we will deal with at quite extensively later. That is one of the very important outcome of this. In my book, when I wrote this chapter, I called realization of from ensemble realization and the fluctuation of chapter, I said realization of the promises, because that's first time StatMech gave, which was done by Einstein, the most remarkable predictions that comes. Okay. So I am asking you a question now. If I give you this kind of thing in a more general sense, many more energy levels, much higher energy, but in the system, that which of the energy is more probable? What is that? There is a distribution which will come out, but all of you know that. You know that from high school days, Boltzmann distribution. So though energy is fluctuating across because of constancy of temperature, there are in a probable distribution of the energy. So when you relax the constraint of constant energy, and as a result of the constraint, we get all these different arrangements or different occupation of the microscopic state and different microscopic states. There is there is a constraint that comes. So we relax a constraint, but you get a constant in terms of distribution. This happens again and again. The same thing happens in the case of grand canonical ensemble or other ensembles, but that is one of the beautiful of these thing. Okay. So, go back, let us see how a constructed Gibbs went around doing it, and this, as I told you, it is a beautiful construction that Gibbs did. What Gibbs said, okay, I assume that all my systems are made at, I put all my systems together, all my NVT together in contact with each other, and then billions and billions of my microcanonical ensemble systems put together, and then I put them in contact, then I put them in a isolated, I put a box around them and isolate it constantly, completely. So, now each of these system is an NVT system. This is NVT, this is NVT, this is NVT. But I have put them in contact, they are NVT, they can exchange energy. So, instantaneously each of these states are in different energies. Okay. Now, from a super ensemble, all of them I put in contact, and I now added the energies of all of them, and it's a very large number of ensemble, and I isolate them. Then I can talk of my super ensemble, I insulate it, my super ensemble is a total number of n. So, I have this number of italicized n, and this is my total number of ensembles, total number of microcanonical ensembles in the system. So now I create an ensemble out of this ensemble. That means now my NVT, each of my system here are at NVT, but instantaneously they are NVT, but they have different energies, right? So when I put them together, I have a huge number, n of them I put them together, then I isolate them, then I make ensemble out of that ensemble, my super ensemble. Then my super ensemble, each of them is consists of an ensemble. They themselves are in having this number of volume and this number of particles, but energy will have a sum here. There is a constraint, and this was then, because the only thing that I have, you have to understand, the only thing that I have is this formula. That's why I said that everything follows from that. The only thing that I have this formula. So now what I am trying to construct, when I go to canonical ensemble, I want to construct an ensemble of ensemble such that in my super ensemble, each ensemble is a microcanonical ensemble, is a microcanonical ensemble. Okay. I saying this is one after another brilliant construction, and it's very difficult to have that. Then what one does, I have discussed it quite a bit here, but I just want to do the math. So now, if I now have in my ensemble, this is the number of systems that have my energy here, then that has to be, this is here, the index is not capital N, it is total number in S, and so then Ni total number. So let me denote this Nj by the number of systems in energy level Ej. So then total number with the total number of things in the energy level Cj are the total number in my super ensemble, and then the population Nj is in energy level Ej, then multiply I get the total energy Ej. So the notation I say, personally when I teach, I actually this italicized n, but here the italicized n has become capital N and capital T. So this is total energy, Ej is energy of one of my system in my ensemble, and I have made, I said, microcanonical ensemble of the ensemble of ensemble, and this is the condition, because this is the total number. So, NS is the total number of systems in the my super ensemble, and this is the total number, total energy. So, each system in my in the canonical ensemble, constant temperature, but they are in a different energy state. Is there any confusion here?
So that means that your bigger ensemble is just the smaller ensembles, and there's no bath actually. I mean, if the total energy is sum of energy of each of them, then there's no bath, right?
Yeah, you are allowed to make the systems interact with each other, and you are giving the condition that they themselves, you keep that system for at equilibrium with long time with a bath, so that the temperature, almost the way we do the simulations, so the temperature, it comes to a constant level at temperature T, then you isolate it, you insulate it completely, and that is the super ensemble. That's how, and then you call that so the ensemble of, okay, number of particles of microcanonical system you put together and construct a system in canonical ensemble, NVT. Then you put ensemble of those things, and that has a constant total number of particles. It is not the number of particles in one system, it is the total, and then energy also fluctuating. This is the constant. Is it clear? This is not an easy construction. But what you get at the end of the day is of a huge importance. This is a very serious business, and usually this thing is not taught in the classes because it's a kind of complicated thing. Okay. Now we are going, as I told you again and again, so we have created a super ensemble which is microcanonical, because I have nothing but this equation to go. So I have to go back to that equation. That's why I have to construct the microcanonical, super microcanonical ensemble, and I am working on the super microcanonical ensemble. So I have the super microcanonical ensemble wherein is the total number of systems. So it's the total number of systems in my ensemble, and total number of system, each of the system has in that energy level. So in my super ensemble there is n1 number of systems, not particles, n1 number of systems in energy level E1, n2 number of systems in energy level E2, and then I can write total number like that. Okay. So I do the combinatorics. Now I can now develop a saying, and this is really extremely important. One can define that probability of observing a given state Ni in energy Ei is this quantity. So here I have done a partitioning. I have said, okay, I have Ni systems in energy level Ei that has, since they are in constant energy, that has an omega associated with it. Okay. So that is this omega. Then this is normalization, because I sum over all the energy levels. The total number of microscopic states is the total, is the normalization. But then this gives me probability of observing Ni particles in the A. So I am done an averaging here. So this is a very important definition in the whole scheme, Gibbs scheme of developing the expression of microcanonical ensemble. Is it clear? So that means you have to think in terms of a little bit, because this Nj, a number of systems at a energy level J. Since the reward you are getting, since you have fixed these things as constant energy, I can talk of this, and it makes sense, because omega is number of microscopic states of a system with a given NV and energy. Alright. Okay. Now, game we are going to play now. So, this is like you can guess what you are going to do. So, we have defined probability of observing a system with a energy E, Ej, and we have the total number. However, we know in the total number there are these two constraints. But so this is not an unconstrained, this is not an unconstrained variable anymore, sorry. So this has these two constraints. So what is the way we do it? So anybody has any clue how to go about it now? Okay, just like before we are going to do a we will do the we will maximize ln omega, and from the combinatorics I get this equation. Any confusion there? Okay. Now I want to maximize this quantity. Any confusion there? However, there is not the way you do that. There is a way to do this. There is a condition called the condition of Lagrange multiplier. When you have a variation but with subject to the constraint, so when I have these two constraints, I have to put these two constraints into my these two constraints. I have to combine with this equation of this equation with this quantity. And do you guys know the method of Lagrangian multiplier? This is known, okay. Okay, this is the method of a constant is a Lagrangian multiplier is called method of Lagrangian multiplier of variation of constraints. You have done that? No, na? Okay. So basic idea is that we have to maximize this quantity. We have to find that distribution of Nj. Remember, Nj is number of systems at a energy level Ej. However, even though I am allowing systems to vary over different energies, there are priorities. Because of NV and intermolecular interactions, there are some energy levels which are more populated. There are some energy levels which are more populated than other energy levels. Actually, there is a Gaussian distribution, and the coefficient of the Gaussian distribution is the specific heat. But that comes later. Those very fundamental things comes later. Right now, we are trying to get, okay, I give you the energy levels, I allow you to choose your energy, but the system has a constraint. System, because of the total energy is conserved in my super ensemble, total number is conserved in my ensemble. The variation, so the omega, that particular distribution. So what I am talking of, this Nj is a distribution, and I am after this distribution. Okay. So Nj is number of systems in energy level Ej. Okay. Let me write down. And I am allowing these energy levels to change because I do not have a conservation of energy or constancy of energy anymore. So those my arrows. So I have many different energy levels. However, my systems prefer certain energy levels. All the energy levels are not a. When you do the computer simulation, what do you see? You see the energy and the energy is fluctuating, but they fluctuate around a value. That value is the average and also the most probable. Now you plot a probable distribution of the energy. What do you find? You find a Gaussian distribution. Who determine what is the average value, and who determines what is the the width of the distribution? Width of the distribution is given by the specific heat. Who determines that what average energy it will be? It is by the intermolecular interactions and density and volume, N and V. Intermolecular interactions, N and V, that determine your. So now those things must be there, put in a constraint, and those are the constraint. So a distribution is there which I have to maximize, but that any distribution will not do. Those distributions obey the total number of particles that I have is constant. I have written those equations here. Total number of my energy in the grand canonical, because after all I will be working in the grand, going back to my canonical ensemble. So the way that is done, picking up a distribution of many distributions. So I have a distribution of distributions, picking up a distribution, out of that distribution is that those distributions that follow this constraint. And this is the method of Lagrangian multiplier. Please read it. I have an appendix on microcanonical the Lagrangian multiplier in the book. So then we do this, maximize with this constant. This is the way to make a Lagrangian multiplier, and then you take this derivative. You get omega. You put the omega, which we did here in the. This is the omega, and you do the Starling's approximation. Okay. And then you get this constraint, and this is just a constant. You can see now in j to the power alpha beta j, and so n j star become this quantity. So this is the YOLO equation, is the equation that comes out from these things. Exactly, that's a very, very good question. Actually, that's an excellent question. So we'll come to that. That's an excellent question. This is the Boltzmann distribution. And you are right, but I'll come to that in a minute. So I think we'll probably, with that answer of a question, we'll stop today. As I said, that's one of the again the questions, just like the questions you guys asked, is a cause of confusion. So, but you are okay with this now, right? Okay. So now I have to get this quantity here, e to the power minus r. So I do sum over nj. If I do sum over nj and I sum over e to the power minus beta j, then I can sum over nj is the total number n, and then this is the quantity, this e to the power minus beta j, e to the power alpha, because this n is the a. So then you get pj is nj by n. From there you get e to the power minus beta j by this quantity is okay, because just I sum over that. So this is the definition that we started to do, the probability of finding a system. So because we work with systems, number of systems in energy level Ej. It is not number of particles in a energy level Ej. It is number of systems in energy level. And so the probability of observing a system in a energy Ej is this quantity, and this quantity is the canonical partition function. And so if I write the canonical partition function here, that I have written later, then this is the one of the most fundamental equation of statistical mechanics, which now tells you how we have not yet shown that beta is temperature, but we will show that beta is temperature. For that we have to do an analysis very similar to what we did with Euler equation in a microcanonical ensemble. That we will do. Now I'll just, before we stop, I'll answer this very good question. What you have to do now in order to get out that, so probability of Pj is Pj is equal to minus beta h Pj. Now what you do, you define the average energy E, and then average energy E is alright, because this is Boyer distribution. It is this quantity which is Gaussian. So now you consider your average energy is this you make a fluctuation delta E, and from here now you calculate that's exactly we will do later, we calculate the variation of energy. So now you say, since energy, your average energy where the system is the one which minimizes the free energy, so first derivative of that goes to 0. So your the energy then it is like that, energy E is E average plus first derivative is 0, then second derivative is d2 a d2 delta E square. So your variation of free energy, and then because first derivative is 0, so now probability in this is e to the power minus delta A, and that is e to the power minus E goes out, and you get e to the power minus delta E square. So a really very good question, that Boltzmann distribution has within it the Gaussian distribution, but this is Boltzmann distribution where you are asking what is the individual energy, what is the population of individual energy levels. Gaussian that you observe is the total energy. So in simulation, when you find a Gaussian distribution of energy, that is the total energy, not the individual energy. Yeah. Not any observed system. When you look at the observed total energy of a system, is the total energy, average energy, or observed energy that you have. This is not the observed energy. This is the one confusion you always have, because when you do spectroscopy in quantum mechanics, we consider this is the energy that you observed in spectroscopically, but those are isolated, single, non-interacting picture. When you are allowing energies to exchange, like in a macroscopic system, so thermodynamic systems, then this is the Pj is the probability that your system is an energy Ej. We use that same there also. But when I talk of Gaussian distribution, it is the total macro variable, total macroscopic energy, that is the Gaussian. And that comes from there by same definition, but you define the total energy by that equation, average energy of that equation, then you say my free energy is the one that is minimum at the average energy E. That property you use, and then you get the Gaussian distribution at equilibrium. At equilibrium. Okay, let us look at that. These are the construct we did, because as I told you, there is only equation that you have is entropy equal kB ln omega. We did the construct, made of a super ensemble which is microcanonical. So we started with the ensemble which is canonical, then we put many canonical ensembles together, and I put a super ensemble, microcanonical ensemble. In the microcanonical ensemble, I now can talk of number of systems in energy level Nj. Then I can do and construct a omega now, and that omega has the constraint of total number of systems and total energy, because I have a microcanonical. So a microcanonical has constant energy and constant n. I put those constraints by using Lagrangian multiplier, and I get that article out. Okay, that is the whole game that he played, Gibbs played. Okay, now you are asking, say, so the Gaussian energy is Gaussian, volume is Gaussian, all these things. So in a computer simulation, we are studying this. You are talking of a single system, but you are talking of a trajectory for a long time. Or you can take a Monte Carlo simulation where you are creating many configurations of the system, which is same as creating many systems. Okay, right. Now you are talking of average energy. So when we plot the energy of the system either along a trajectory or in Monte Carlo, and I have a histogram. I have this many energy, this many time my system is in this energy. But that is the macroscopic total observed energy. This is not what you observe. This is what the microscopic occupation of the system. And we find out from this distribution what is the energy, average energy, that just what I wrote down, we will do it tomorrow, and what is the entropy, what are the other properties. We have not done that. We have just like in microcanonical ensemble we have got that important equation. That is a Boltzmann distribution. And from there now we will construct the rest of the things. So that we will do tomorrow 10:30, right?